Okay. Really important, very, very important idea is total expectation. And this takes some practice working with it, I think, to get it under your belt. Even though the idea, just actually like manipulating it algebraically, even though the idea is very simple, and the idea is that the average value of a random variable in a total population is the average of the subpopulation averages. You just have to weight by the stratum prevalences. So you can average by first grouping people and taking averages in those subgroups, and then averaging those subgroup averages. And we can see this, so just bear with me for now. Like we have, again, our total, our marginal expectation, which is the sum of all the measurements in the population. And we can break that up, okay? So let's break that up into this little notation here. You don't have to worry about it too much. Basically, I'm just saying take all the people where the value of y is equal to little y1, and then take all the people where the value of y is equal to little y2 and y3. And so I'm just breaking up this total sum into these three sums, or really, however many values that y takes, I'm splitting it up like that. And then this 1 over n is just a constant factor that comes out in all of them. And so the sum is like what's in the numerator. And now I can multiply each of these sums, top and bottom, by however many number of people have this value y1. So that's an ny on top, and then I will get a 1 over ny. Let me write that in actually, in case you're not following. So I'm just multiplying this by ny1 over ny1. Okay, which is 1. So I can just multiply this by 1. It does nothing, right? And then I'm getting this fraction, and then I notice that this thing over here is exactly this conditional expectation. That's just the definition that we were using before. So I do that for each of these sums, and we get something that looks like this. And now we just have to recognize that these things here, the ny2 over n, ny1 over n, this is how many people have y equals 1 out of the total population. And that's just the probability that y equals 1. Similarly over here, probability of y equals 2. So what we have is probability probability that y takes some value times some function of y, okay? And then all added together, which is the definition. We know when we are looking at you can think of this thing here, right? This is like a transformed random variable, where if somebody in the population has value y, now I mutate it to give you the value y given that, say, little y goes to this, okay? So it's just like it's a mutate. So this is like my g function. And so what we have here is if this probability is like a density, probability of y, and then this thing is like a g of y, right? So we have this sum like that. That's what we're getting. So that's what I have here. So this is the marginal density of y times this conditional expectation. And you should recognize this as the expectation of this function. Okay, so this is a function of y, and this is just the expectation of that. So that is the expectation of this conditional expectation function, where the notation, again, like I said, you have to work with it a bit to kind of follow exactly what's going on here. But think of this, right, as a new variable z, right, where I put in y, and then this tells me what z is, and then here we have expectation of z. So we've shown that this kind of follows through like this. So this is super important. This manipulation is used all the time in probability and statistics, and we'll apply it a little later in the course when we're talking about conditioning, how to recover causal effects from observational data, identifying causal effects. Is absolutely everywhere. So yeah, a little bit more of a notation here. You can think of this thing here, right? This is a function of at a particular point, little y. This is a fixed point. And when I write it down here without the equals y, this becomes a random variable because this is at whatever y is for that person in the data set. So another way to think about this is in the population data. Another way to think about this is like this thing is a fixed function, right? This conditional expectation function. Y is a random variable, so it's like the measurement of y on this person omega, okay? And you feed that into this expectation function, and then when you average over all of that, it's clear that this has to be averaging over all the different people in the data set, okay? Here, there's no people, right? This is just the function mu of x given y at a particular value y, all right, which is given by wherever what we're looping over. Okay, so again, backing up, total expectation. This is the bottom line result. The average value in the population is the average over subpopulation averages. And you can also do this if you've already conditioned. So if you have your average value within a stratum of the population, that's the average value. That's the average of averages within substrata. And now you just have to weight by the substratum prevalence. What I mean by weighting is that we have, so here, right, you have, this is the population average. These are the subpopulation averages here, right? So you're not just adding them together. They're weighted by the prevalence of this thing, of these different subpopulations. So for example, if the number of people with Y1 is very large, like not large, like 90% of the population are Y1, then it's going to be 0.9, and your population average is going to be a lot closer to the subpopulation average where that thing happens, because these numbers are going to be small. It's going to be 0.1 or 0.05 or something like that. So the subpopulation averages within the strata will be downweighted, which makes sense because you can't just, if some strata of the population are very rare, then you don't really care about what the average age in, I don't know, like, here's a concrete example. Like, what's the average age in Europe, or like just Western Europe? Well, you can find the average age in France and in Germany and in Spain, and those are relatively large countries. And so your average age across Europe, Western Europe as a whole, is going to be close to the average age in Germany and France and Spain. But let's say that let's consider a country of Liechtenstein, which is a tiny, tiny country. Not a lot of people live there. Let's say that the average age in Liechtenstein, or like really high, a bunch of old people live there. It's like 50, 60, something like that. Is that really going to change the average age in Western Europe? Not really, because there's just not that many people there. So the population average is a weighted sum of the subpopulation averages, and the weighting is precisely to get the averaging to work out right at the population level. It's these probabilities, which is why you get this density here. All right, so maybe I beat that to death, but let's work on a problem, and you'll see how this is applied. Let's say x is -1 with probability 1/3 and +1 with probability 2/3. And I've given you the conditional expectation of y given x, and I want to know the expectation of y. So you don't really know much about y, you just know the conditional expectation. Y could be, at each value of x, y could be normal, it could be uniform, it doesn't really matter. But this is actually all you need to know the marginal expectation of y. And the reason is that this follows from total expectation. Okay. So here we know what this is. And now, well, there's a couple of things we could do. So let's use total expectation again. So let's say given x equals little x. You may think, okay, what the heck? Why am I conditioning a thing on? Well, you can. There's nothing wrong with this, right? It's just saying what's the average value of this when x equals this, and then I'm averaging across the different values of x. So this from our function based on the densities, remember, is you're looping over values of little x. And in this case, it's just two values. It's 0 and 1, right? Because x can only take, or sorry, minus 1 and 1. Minus 1 and 1. And then we have the density of x, those values. And then the function that's being averaged over is this. Now, this will hopefully illustrate why I've written it like this, because let's say for for x equals minus 1, we know the probability of that is 1/3. Okay, so that's I'll just say f of x at minus 1. Okay, and now what's g at minus 1? So that means when x equals minus 1, what is the expected value of x plus 1 squared? Well, if x is minus 1, I know that x plus 1 is 0 squared, right? So this thing is 0. It's a constant, right? And then I have the other case at x equals 1. And by the way, I know this is 1/3, right? And I know this one is 2/3. And the value of this when x equals 1 is 1 plus 1 squared is 2 squared is 4. Is that right? Looks right to me. Okay. So the total expectation here is 1/3 times 0, 2/3 times 4, so it's 8/3. That's the population mean of y. So that was one way of doing it with a total expectation. I could also have done it more kind of like brute force, because this is just a function of a random variable, right? And so it's the same thing, but here I can do f of x times whatever that function is, little x plus 1. This makes a bit more sense, but I wanted to just demonstrate like kind of the conditional expectation conditioning on the variable that's already in there. You're gonna get the same thing. So here this is multiplied. So again, you're gonna see that when x is 1, this is when x is minus 1, it's 0, and then otherwise it's 4, and you're gonna get the same thing. So this is summing over minus 1 and 1. So because of the linearity of expectation, you can always write a random variable as the sum of its conditional expectation and some other stuff, which has mean 0. So that's what I'm showing you here. So let's define. So let's start with x. X is some measurement, like height. Okay. So I define then r as some other measurement. Well, first I get what is the mean height in each country. Okay. And now for each person in my data set, I subtract off from their height the mean height in whatever country they live. That's kind of what this is doing for the population data. And then I mutate that into some other variable r. Okay. Now if I have that other variable r in my population data, if you take the population mean of it, it's going to be 0, exactly 0. And the reason is because of linearity of expectation and total expectation. Because if I'm asking about expected value of R, that's the expected value of X minus this. And by total expectation, we know that's exactly this. And so these cancel and we get the 0. So I made this new derived measurement. And another way I could move this whole thing to that side, and so I could just say, okay, instead of writing X in my data set, I'm going to have two variables, one of which is this conditional mean function, which is a deterministic thing that just based on the country, it gives you a single number, and then some other random variable, which has a mean of 0, and encodes kind of like the randomness in the population. So it's a way to decompose the randomness into what is the randomness that is due to what country you live in, and then what's the other junk, right? That just kind of gets added on. So that's kind of nice. Nice way of thinking about things often, because you can, for example, write your simulations like this. So if you have a variable y, here it's a uniform, and then I can write x, and I want x to have a particular relationship with y on average. Like, if y is age and x is blood pressure, I'm thinking like maybe blood pressure increases linearly with age. So I want this conditional mean relationship to be linear. So I would have like a times y or something. Here I'm doing something else, sine of y. Okay, sine of y squared. But then there's also a bit of noise, right? People's blood pressure is not entirely deterministic based on their age. So all I need to do is add a little bit of noise here. And so this is a very common way that you'll see people write simulations, that they, instead of directly writing what is the, we already saw from factorization of density that you can write each part of the density, right? That's what the structural equations thing is kind of doing, right? You're saying marginally, what's the distribution of y? And then you're saying conditional on y, what's the distribution of x? And what I'm showing you now is that you can break that up even a little further. Instead of saying what's the conditional distribution of x, you can say what's the conditional mean of x? And then what is this noise that's being added to that? And that fully specifies the conditional distribution of x given y. And so it lets you break down the problem of like thinking about how the data are generated even more finely.